Okay. Tuesday, week 7, scaling. I mentioned again, we talked a little bit about change, grit, drive, metacognition, and I'll go over that on Thursday. At least give some resources. We talked about dynamic routing, and then the students worked on the class lab. I think if they had their druthers, they would just do this. Anyway, let's take a look at a couple of things we did. Alright, so this is a repeat of the first page. Next. Routing. So we talked about, in order, so if you even take a look at something like this, in order to have connectivity through through arranged networks, right? You're going from one network, I guess I should make this more simple, one network to another network. To understand that, obviously you have to understand IP addressing a little or a lot. Okay, so we want to find the best path. That would be the network layer or the internet layer in the models. The best path to get from here to here. And in our world, a lot of it, we have a client, we want to get to a server to get data. Data is the key in all this. So what's the best path to do that? Through moving from networks to networks. So we have a cost, and in our scenario the key here is that cost, we want the cost low. Okay, so we use metrics, some type of way to measure a cost, and we can do how many hops, router to router to router. We can go bandwidth, makes a lot of sense, bandwidth, primarily OSPF. How much delay, that's load, it looks like bad, that's load, and there could be other metrics. Just jumping up here, EIGRP has a lot of metrics, RIP is hop count, and OSPF is basically bandwidth. And EIGRP uses a couple of metrics, but what they do is they come up with a cost, and the lowest cost wins. That's the way we're going to go. So, interior gateway are within autonomous systems, and we went through this. Like, let's say, NIAC. I have NIAC listed here as a great big network. It's not, but let's say NIAC was across the whole United States, like Walmart. Well, Walmart would be across the world, but we have a big network, and we can be dual-homed, multi-homed into different ISPs. So if one ISP, and later on we talk about the efficiencies here in connecting networks. And so we are, let's say, running OSPF. Then there's a middle-sized company, maybe they're running EIGRP. This is an autonomous system. This is an autonomous system. So we have another autonomous system here, a simple network. Maybe they were just running RIP for the advantages of it's simple, not much load on the routers, etc., etc. They have a small network that doesn't experience changes, very seldom, pretty set. So they're just connected to one ISP, whereas our middle and our big network at NIAC are connected to two ISPs. Between autonomous systems, between autonomous systems, we're running some type of border gateway protocol or an exterior gateway protocol. BGP would be most of the time runs for those. Okay, so we can be running BGP between autonomous systems. Now you might say, well, you're not running BGP here. Well, we have a simple scenario here where we can just point to this network and default out. More on that type of information, okay, more of that will come later on when we do more WAN work in a future course called connectivity. Okay, so from this you should understand what we mean by an autonomous system and interior gateway protocols and exterior gateway protocols. Up here we talked about distance vector. Communicate with your neighbors, so you really just take the information from your neighbor. These two are distance vector. Okay. Link state, you actually build a table that then eventually gives you, I'll just call it a map that looks at, you see the entire network, and then from there you can build this tree of best paths to all the locations, and then the correct exit route can be put in the router. So that's true for both of these. The best next hop is put into the router. Where is the router going to send the packets next? And when all of that's been set, everything is seeing a true look of the network, you can say we converged. So getting to convergence is important, more important for some networks than others. You take a company that streams, so to speak, for a living, like Netflix, or it's a good example, Netflix and other ones, or online businesses. You know, if they have a change in the network, then they have to dynamically have it converge quickly in order to recognize the change. So if you have a whole map of everything, that helps. Now, how do they know these can be triggered by some change? Or RIP, at least the older versions of RIP, would just use a update time. So like every 30 seconds they're going to send new tables everywhere. That's a lot. Let's keep moving. Oh, this looks familiar. So this is Chris is working on a project at home, and this is the project here on campus. So from here we have, so I mentioned briefly classful. This is just for legacy information, because pretty much everything we're doing now is classless. All the routing protocols, we're doing variable length subnet masking, we're doing classless inter-domain routing, okay. But how it used to work, if you had a class A address, then you could see here the router really actually only needed to look at 3 bits to figure out where to send something, because everything was divided by classes. This was a class A. If there was a 1 there, it was a class B. If there was a 1 and a 1, a class C. And if there was 3 1s, it was a class D. So you can see how that worked, except there wasn't enough addresses to keep doing that. So they went back and created private, right? Actually created private addresses, and then split this all up and took back a bunch of addresses from people like IBM and so forth. All right. So here's our project. Here's some addressing. Just FYI. That is it.